Hey guys.
All right, so my name is Niklas. I'm a product manager on the WebRTC team. Excited to be here today with my two great colleagues.
Yeah, so my name is Huib Kleinhout. I'm also a product manager. I focus on the Chrome platform.
And I'm Justin Uberti. I'm one of the founders of WebRTC and the engineering lead for our WebRTC team.
So I'm happy to kick off that presentation by sharing this year what we call the path to 1.0. So what exactly do we mean with 1.0? There are four different aspects. One aspect is to help and work on finalizing the specs. The second one is to provide tests for those specs across different browsers for the ecosystem. The third one is to implement, finally, the missing specs inside of the Chrome platform. And the fourth one is to get rid of bugging reliability issues that we still see in Chrome and provide really a stable foundation to the ecosystem. Why is it important to us to provide this? We see the ecosystem really growing over the past years. So I want to kick off that presentation with looking into some stats. We see over 1.5 billion combined audio and video minutes in Chrome right now from users that opt in into providing that information to us. And I was super excited last year standing here and presenting the 1 billion number on weekly averages. And this year it's a 45% increase that we are seeing. So it took us 4 to 5 years to reach the 1 billion, and just in 1 year, basically, made another 40% of us. And it's not us, it's you, basically, the service providers and services that launch their services and make use of WebRTC and Chrome. And this number is growing too. So 1,300 projects and services that build on WebRTC now that we are tracked by our friend Sahi. And that's another 10% increase from the numbers that I presented last year here. And it's not only the 4 browsers that we had last year, there's a 5th browser that came, and we've been super excited to see Safari basically joining the WebRTC bandwagon. So all the big 5 browsers are now supporting WebRTC, and that basically comes to an 80% of all installed browsers that have WebRTC built in.
Woohoo!
Woohoo! Yeah. We had a big party when that happened. People were dancing in the office. When we look a bit from a developer perspective, and this is data that we have in WebRTC.org, you see like the top countries is United States, but like the second and third largest countries of visitors on WebRTC.org are China and India, and both of those basically have the same amount of hits on the website as coming from the US. So these are 55,000 unique monthly impressions that we have. And interestingly, when you look at it, what is it actually, what are the most important topics on WebRTC.org? You see number 1 is actually development for Android. And number 3 is a native development for iOS, basically more or less equal. So we see a shift here from what was originally targeted to be a web-based and web API-based platform for real-time communications into developers adopting it on mobile and building natively for it. And that's why we went out and about 4 to 6 weeks ago, we published mobile developer libraries. So there's an AAR Android archive out there, and there's a Cocoa pod out there. And the Android archive has seen within these 4 weeks more than 2,000 downloads already, and that's just after 1 month. And very similar to the Cocoa pod, we've seen 1,200 downloads and 300 unique projects that build on these mobile libraries. So the ecosystem keeps on growing. We're super excited about this. But the mission for us is basically to provide this stability and reliability. And Huib will start walking you through some of the topics here.
Perfect. Yes, so WebRTC 1.0. This has been a long journey, like 6-7 years ago, started by Justin here and others to create real-time communication through a standardized sets of APIs on the web. And now we're finally getting there. And as Niklas pointed, we're working on 4 areas: finalizing the specs, making sure the browsers, and from Google's side, that's Chrome, are compliant, ensuring we have good tests, and making sure that everything is reliable. Altogether, this makes it possible for developers to easily develop web applications without ugly workarounds like adapter.js, which works around all the clutches and differences in browsers. And for users, that when you start your browser and open Facebook Messenger or Hangouts Meet, that you actually can make that call without interruptions and audio not working. So this complex set of technologies are standardized in a bunch of specs. This effort has been going on for the past 5-6 years. This includes existing standards and RFCs, and to some extent new standards and extensions to it. And now we see that finally all those pieces are coming together. Either there's already consensus and they're standardized in RFCs, or they're reaching this state within the upcoming months. So we finally have this package of all the components we need to make these video calls across the web and across all the different types of networks together. And yeah, of course, the different browsers need to be compliant with those standards. And Chrome was one of the first browsers that implemented the WebRTC APIs in JavaScript. And this was 5-6 years ago. And over time, the APIs has changed, the specification has changed. And Chrome hasn't always been updated. There's also new browsers implementations. So that's why we have adapter.js. We have like all these differences. So we're very committed in Google to make sure that everything in Chrome gets now completely aligned with the 1.0 version of WebRTC. The last month we added like get stats to get all the metrics of your media streams. Introduced the spec compliant media track constraints that allows you to in a more sophisticated way get microphone and video camera input. And we started implementing the RTP Media API, which is like the latest generation in the WebRTC spec. Some of it is available as a command line option in current Chrome version. Some of it will be coming. And most importantly, a unified plan SDP, which is the way to describe multiple tracks and streams in the SDP. This will be, we expect to land this like early next year in Q1 in 2018. So we have all these things together to be on the same page with the other browsers. We know WebRTC is a complex piece of technology, but browsers are even more. They have like tons of history and tons of technology. So to be able to make sure that browsers consistently implement the APIs, there's an industry consensus on how to test this. It's called web platform tests. Over the past months, we made a complete test bed for WebRTC in this web platform tests, and they are run automatically every night for the nightly builds of the different browsers. Currently, it's very red, as you can see. This needs to be green, but on the good side, it's very red because there's the automatic runs don't happen with clicking on giving access to the microphone and camera, so a lot of the tests fail to that. So we're going to fix that, make sure that the tests are run properly, and make sure that we implement those remaining APIs. So this will be all green, and as a web developer, you know that like if I access this API, it will work in all these different browsers. Now, web platform test is one part, which is used for testing HTML, CSS, and all those W3C standards. But WebRTC is a bit more complicated because you don't have just a JavaScript layer talking to a browser. You have different browsers talking with different browsers and different operating systems, and in many cases even an SFU, an intermediate party. So it's a lot more places where it can go wrong, lots more protocols that can be incompatible with each other. And to be able to test that piece of the system, we embraced a proposal from the community, from Alex Gouillard, one of the WebRTC experts, to develop a test system where you can test these different connections between different browsers. It's called Kite. We send out a message on Discuss WebRTC announcing it, and it's an open source piece of code on GitHub, so anyone can check it out and make modifications and contribute. And with these tests, basically, you can run browsers in different virtualized environment or in physical hardware, and these browsers will make connections with each other. And if there's a success, it will be reported to a dashboard. This allows anyone in any situation in any kind of system to test WebRTC more as a whole system. And we will be extending this test tool in the upcoming year to embrace more test scenarios. And you can set it up in a local way or in a virtualized environment, for instance, on browser stack. So with all these test frameworks together, like web platform tests and Kite as an overall ISM test, we want to make sure that the browsers, not only that we reach this compliance, but that we also keeps working in the future and we get alerted when things start to break. So yeah, with that, we go to the fourth component of our WebRTC 1.0, which is reliability.
Thanks, Huib. So this is kind of a hard presentation to give. We've got Twilio up here demoing video chat and AR, and I'm basically going to tell you we fixed our bugs. So this stuff is really important, though. Like, the difference here of reliability is the difference between having a productive meeting and saying, can you hear me? Please mute. The presentation's frozen. So we're making a really big investment here. We've really invested over the past few years in a lot of things around quality, bandwidth estimation, signal processing, codecs, that sort of thing. But we're also sort of investing in the fundamentals of making sure things start up, and if things are wedged in the operating system somehow, that we can restart them to make sure that audio starts every time, video starts every time, and the core things deliver that enterprise reliability so people can depend on this in all their applications. So we've made good progress over in this area in the past year, and I'll talk about some of the specific examples. So Chrome 63 has a lot of great stuff. It goes to production in December. That's the TLDR. But these are all areas where we've made significant improvements to Chrome's reliability over the past year. And I'll talk about several of these things in detail. This is actually an issue that's been a thorn in our side all the way back to 2012. And frankly, it's a little bit embarrassing to me that if you look at the statistics, and we didn't really realize how big of an issue this was until we finally instrumented it a couple years ago, and found that in Chrome Stable, like 8% of the actual get user media mic calls failed on the Mac. And many of you who have WebRTC applications on Chrome probably have had customers complain about this. And we dug into it, and we found that basically it was very hard to reproduce, first of all, because it wouldn't happen right away. It would only happen in weird cases. And secondly, it seemed like it was an issue down in core audio. And where basically core audio would just give us a stream that had no data in it. And so we weren't quite sure what to do until finally we had a developer who was like, I'm just going to fix this. And he dug into it and spent a ton of time and finally figured out there's a race condition. That sometimes when you put a Mac to sleep, you would get basically an event for suspend before the event or after the event for resume. So we would get kind of confused and think that we got resume and then suspend and think that the machine was still suspended, the audio should still be suspended, even though it was actually awake. And so the only way to fix this previously was you actually had to reboot or restart the whole browser process, take down all your tabs, bring them back up. But now we just basically made a small change here to move to a reference count, and we can now recover from this issue. And if we have it in Chrome Canary, you see we're basically reducing the impact of this issue by over 30x. And in actual stable Chrome, where browser runs for much longer, people have it open for more time, it's going to be through more wake and suspend cycles, we're going to expect to see even larger improvements. Now, we haven't fixed everything until that number is 0, but there's more things I'll talk about how we'll get that last remaining set of cases fixed in a few slides. So, also in Chrome 63, Per was here from our audio team to talk about the new AC3 algorithm about a year ago. And I'm here to say we're getting ready to roll this out. AC3 brings a bunch of improvements. It's more flexible. It deals with glitches. It deals with clock drift. It deals with all sorts of things better. But it also, in addition to removing echo better, it does a better job of not trying to alter the signal when there is no echo. That's what's called better transparency. And so we've been testing it over the past year, tweaking, tuning, making lots of improvements. We're now getting ready to roll this out to the broader ecosystem in Chrome 63. And again, we think this will make a big difference in the sort of, please mute, echo type of situations. So another one is screen sharing. Again, this didn't happen very often, but we had a number of people complaining that sometimes it took a long time during screen sharing for slides to update, or generally keyframes would get stuck. And we looked into this, and we found that the 50th percentile was fine, but the 95th or 99th percentile, we'd see really, really large outliers. And when we dug into this, we found there's this phenomenon of what would happen is we'd send a keyframe, and the keyframe would get broken into many packets, and one of those packets would get lost, And it would take a long time for that to get communicated. And so what would then happen is, hey, we'll fix it. You know how we'll fix it? We'll send a new keyframe. And so we send a keyframe, and then one of the packets will get lost. And so then it would take a long time for they to get back to us. And we say, hey, I know how we'll fix it. We'll send a new keyframe. And so one of the packets will get lost. And then we try to fix it, and so you get what I'm saying. And so what we end up with is this thing where we can see 20 seconds sometimes for slide changes. So we kind of tweak the algorithm for how we recover, especially in screen sharing modes where you have very, very large keyframes to deal with this sort of case. We've now brought this 99th percentile down from almost over 20 seconds to 2 seconds. So I think screen sharing should be, again, much more reliable, much more stable. Chrome 63, December. All right, so I talked about more stuff coming on the audio side. How can we deal with more cases where something gets wedged deep down inside the audio subsystem without having to restart the whole browser? Well, the great news is that Chrome is a multi-process browser. So it's good at spinning up different processes, render processes for each different tab. We can also spin up a new process just to handle audio handling. And so what happens then if the audio process crashes? No problem. We'll just go bring it back up. What happens if something gets wedged? Well, we only keep the audio process around while we actually are using audio from Get User Media, so that thing will have a finite lifetime. We can bring it back up and bounce it without having to restart the whole browser. Now, what's the downside? Well, it turns out there's a ton of tubes and wires inside the audio process for dealing with the audio element for YouTube tip scenarios, for web audio, as well as for WebRTC. So this has been a pretty complicated rewrite to basically take all this stuff and carefully dissect it and move it over to the audio process. But we've been working on it for some time. We expect to have this in the next 6 months, and this will sort of, again, resolve that sort of last, 10% or 0.1% of issues, I should say. They get us from the 2 nines to the 3 nines, and again, providing that sort of rock-solid audio reliability. Because if you can't hear someone or you can't actually turn on your speakers, the call's not going to be any good. So last, I just talked about what's coming for audio. Well, we actually have it right now as of Chrome 62, which is current stable version for video. And what we did was to sort of dissected the video capture code, moved it to its own process. So any flaky webcam drivers, they crash, no problem. What you just see is the process goes down, the application sees that the media stream track just got ended. The application can just seamlessly restart it, boom, everything's back off and going again. And I'm going to show you a little demo here of how this works. And what we have in this demo is we're going to run Chrome with a little flag that says, actually crash the video driver, a few seconds in. And so what you're going to see is first, when we run it without the running in a separate video process, you're going to see the whole browser go down. And then we're going to run it again with the new stuff we have in Chrome 62. And what will happen will be you'll just see kind of the video stream stop, but then it gets easily restarted by refreshing the page, and off it goes. And so let me show this to you. All right, so they're getting ready to launch it here with the crash after 100 frames. There it goes, and bye-bye browser. All right, it's not cool, but here comes our hero. All right, we multi-process mode engaged. All right, here comes our crash, and whoop. Okay, the browser stays up. This just, you see here just that there's the thing in the console saying the stream ended, and the application could restart at that point in time. Here they've just chosen to refresh the page, boom, and off it goes. So this is the kind of thing where we're building this extra redundancy, this extra sort of way of dealing with problems into Chrome so that we have the extra line of defense to make sure even if something gets broken within the operating system, within the driver, we still can maintain high call quality and high call reliability. Whoa, okay, better fix that.
Tomorrow.
Yeah. I'm going to check for your TBS report. All right, so PSAs. A few things that have been posted to the WebRTC mailing list that I think are pretty interesting over the past couple months. I'm going to just talk about some of these in detail. I recommend, to get the full detail, going back and actually clicking on the links we have here, or going back and looking at the mailing list because there's a lot of nuance. The first is injectable audio codecs. We've heard requests for years for people saying, I want to use AMR, or I want to use my own special codec, or I need to run this on some embedded device. Can you make WebRTC smaller? And their answer now is yes, you can. WebRTC now takes like a factory that says which codecs you want as part of its initialization. So you can either add in additional codecs or strip out ones that you aren't actually using. So it gives you a lot more direct control over this. This is again, for the native environment, not for the Chrome environment, but it allows you to have much more control about what you're actually producing. And for AMR, it can provide some interesting interoperability things and leaves the licensing out of it, at least for us. Second thing, simulcast and SFUs. This is a very confusing topic. We have spent a long time debugging lots of weird problems where people say like their video stream got stuck. And what often we see is that there's multiple streams coming in, and there's like a single output stream that maybe is going to reflect the active speaker. And so like what a SFU might do in the simple case is just take the packets coming in from participant A, feed them into that output stream, and then all of a sudden participant B becomes the active speaker, and the packets coming in, now we just start forwarding packets from participant B. Well, what ends up happening is that the timestamp for participant A's packets were maybe like 1 million, and then participant B's packets come in, and they have a timestamp of like 500,000. So all of a sudden we've seen things go back in time, and our jitter buffer gets confused and says, oh, our last packet was 1 million, and here's this packet for 500,000. Let's go wait for 500,000 milliseconds for that next packet, leading to a stream freeze. And so a lot of these rules are kind of complicated. They don't just affect the timestamp. It also affects the sequence number, which is important for detecting packet losses on the downstream link, as well as VP8's picture IDs, the TL0 IDX, which basically indicates which is the sort of temporal base frame, as well as the TIDs, which are the temporal indicators, temporal level indicators within the stream. And so like this post basically tells you like which things need to increase, which things need to be causal, meaning the timestamp just needs to be like increasing monotonically, and which things need to be held consistent, like the TID and TL pic IDX. So more details about this, but I think this should help resolve a lot of this confusion that's occurred with simulcast and SFUs. Next, on VP9, we've talked about VP9 for a while, and like this is our next generation codec. Fantastic improvements, 35% visual improvements, or 35% fewer bits. We have it on by default in WebRTC. We're very, very excited about this, of just like the quality it brings, especially at 720p. But most exciting is we've made huge improvements in terms of the actual computational efficiency over the past year. We've had a bunch of experts working on this. They've reduced the encoding time by like over 35%. And so now basically VP9 can give you essentially 35, 40% better visual quality, or that many fewer bits, with only 15% overhead. So this is great because Moore's law keeps giving us like 100% better CPU efficiency year over year, and yet here we're giving you like making things even more efficient by meaning VP9 can almost run within the same performance envelope as VP8. And this also exists for simulcast. We've had huge improvements on VP9 simulcast, so it's also within 15%. Actually, the last thing, more like 10% now, VP8 simulcast. VP9 is really ready for prime time. I encourage everyone to start sort of considering this in their migration plans. And also on ARM, and other big speed-ups on ARM as well. ARM is still a little bit more spendy, but again, VP9 for these very, very low bandwidth scenarios, I think is a very, very effective tool. And last, our next generation codec, and this is one of the things I want to be careful not to like Osborne myself here by saying like go to AV1 and skip VP9. But AV1 is like a fantastic sort of cross-industry effort. We have this consortium, the Alliance for Open Media. We are a partner. We also have Microsoft, Netflix, Amazon, Cisco, others, and it's a fantastic sort of thing because I think that whereas VP9 saw a lot of adoption on the server side for streaming. As Facebook mentioned earlier, a lot of the encoders we have are, especially hardware encoders, they're shipping on devices, are not really set up for RTC scenarios. They're set up for like camera type scenarios, and they're not really good at low bit rates. And one thing that's great about AV1 is it really has been targeting not just streaming, but also real-time scenarios, not just like software encoders, but also the hardware encoders. And so it's going to be RTC ready from the beginning. It's a whole different RTC working group happening inside the Alliance for Open Media, and they're making fantastic progress. And so we're finally at the stage now where we're getting ready to have a bitstream freeze. AV1's ready to become not a theoretical thing. It's going to become a real thing. And we hope to see like the first sort of WebRTC integrations for AV1 in 2018. And so like doesn't mean it's going to be tuned out, it's going to be running as well as VP9, but it is the kind of thing where like, if you're building a product and you're kind of looking a year or 2 years out, you're looking at like where's the silicon for this going to start showing up. Like the momentum is all sort of building around this, and definitely AV1 is something we're starting to think about. What does it mean for your architecture? What does it mean for your SFU? These sort of things in 2018. And since they use, it sort of, it has input from many, many companies, but like at its core, it sort of is the next successor to VP9. A lot of the sort of packetization and sort of techniques that were used for, the bitstream and SFU behavior will be very comparable to VP9.